how do we know if that is an acidic hydrogen or not?
Based on the conjugate.
We can look at the conjugate base and do comparisons to something else. Okay? The absolute be-all answer for figuring out if it's acidic or not is looking at what I think Jen just said. No, okay, I don't know who said it. pKa's, oh, it was Tyler. pKa's. We'd have to look up the pKa for the amine to figure out how acidic it is. Anybody know the pKa for the amine? Is it really 30? I thought it was 24 or 25.
I just threw a number
Oh.
out. I knew it was about water.
I wasn't actually surprised, or I was hoping no one actually threw out a number because I'm not positive. I think it's in the 25 range. Okay. What does that mean about its acidity? How do you know not very acidic? What's low? 25 is a heck of a lot smaller than 50,000. True. Negative pKa's are even smaller.
It's a logarithmic scale, so each number is a base 10.
Okay. That still doesn't explain where my threshold is of it being an acid versus a base. What are you suggesting here? Neutral. Okay. So you're looking at water, which is what you guys were suggesting. What is the water pKa? Water's pKa, or really alcohol functional group pKa, is about 16. Is water a strong acid? No. Okay, it can act as an acid, but it kind of has to get forced to act as one. Amines have a pKa of 25. If water's on the borderline between acid and base, what is the amine? It is absolutely not an acid. Okay? To make it act as an acid, we really have to throw in a really strong base to deprotonate it. Okay? So when we look at the amine chemistry, I appreciate that you're saying the difference in electronegativity between hydrogen and nitrogen. It is not a good acid. So that disappears. Okay, so then what do we see? If it's not a good acid, maybe it's a good base. Okay? Methane, is it a good acid? No. Methane has a pKa of somewhere in the 50s. Does that make it a good base? No. What do we need to be a good base?
Higher pKa.
We need electrons. Does the nitrogen supply electrons? Yes. Because it has electrons and a relatively high pKa, what does that mean its chemistry is? We do have this basic characteristic. Not stupidly strong, okay, but it is relatively strong. So we do have a basic nitrogen coming in here. What other chemistry do we potentially see?
It could be nucleophilic.
What do bases do? Share electrons with hydrogen, or accepting protons. What is a nucleophile? Sharing electrons. So if we identify a basic site, what else have we identified? A nucleophilic site. Okay. Do we have any other potential chemistries? What's that? What about its leaving group ability? So really what you're saying is that carbon is electrophilic, right? Okay. Well, if that was oxygen, its leaving group ability was crap. Okay. And that's because oxygen was leaving charge, too small. What do we know about nitrogen?
Smaller than oxygen.
Same row, so its size is ballpark the same, so I don't accept size. It would carry a charge just like the oxygen. Would it stabilize the charge better? Well, size, no. It's less electronegative, which suggests no. Which means, what is its leaving group ability? Not very good. Do we actually have an electrophilic site? Not really. Okay. So we really only have these two primary characteristics, basic and nucleophilic. Could we potentially do something to change, either enhance or stifle those characteristics? We could protonate it. What happens if we protonate it? If it's protonated, it's now positively charged. It increases its leaving group ability. So that's a reasonable option. Okay, what else could we do? What could we do to minimize it acting as a nucleophile?
I'm confused why you're saying it's not a good leaving group when you're comparing it to oxygen. Why are you comparing it to oxygen when there's no oxygen there?
Which is a better leaving group, bromide?
Yeah.
Anybody answer that question for me? Which is a better leaving group, bromide?
So it's just not a good leaving group.
There's no comparison.
That's why I was confused why you're
Okay.
saying oxygen.
So why did I bring in oxygen? So we have something to compare it to.
Okay.
Oxygen was a bad leaving group. We now have nitrogen. How does nitrogen compare to oxygen as a leaving group? It's worse. So it's a comparative effect. Okay. How could we prevent it from acting like a nucleophile?
Haven't used it. It's
If we deprotonate it, what happens? It becomes a better nucleophile, so it didn't quite work. So we could add protons to it. Okay. I want something else. I want to keep that lone pair, but I want to make it a worse nucleophile.
Put it in a solution that's
Both the attachments.
Say that again?
Both the attachments.
If I put carbon chains on that, how does that affect its ability to act as a nucleophile? It makes it worse. Why? The whole point of a nucleophile is getting in and reacting in the center of a molecule. Well, the center of a molecule is in the middle for a reason. There's a bunch of crap on the outside. That crap is electrons. Right? If I put a bunch more electrons around that nitrogen, can it act as a good nucleophile? No. So if I can change those other groups, I can minimize that nucleophilic character and it becomes primarily a base. Okay? So we're looking at how we can adjust and tweak that functional group to change the chemistry and what we can do with it. Kind of makes sense? I'm going to accept that. So let's just do our standard nucleophilic substitution. We said it was a nucleophile. Let's take amine and react it with bromide. Okay. What happens? We just get our standard substitution. Leaving group leaves. We can deprotonate. How would we do that deprotonation step? Right here. We've got that protonated nitrogen. How do we get rid of that hydrogen? How can I use the amine?
because there's more than one.
Number one, there's more than one molecule every single time we run a reaction. Okay? So there is more of that NH3 floating around. What was a characteristic of the nitrogen? It's nucleophilic, which we just saw, and it's basic, which means it can deprotonate. Okay? And I could end up with the primary amine. Okay? I end up needing two equivalents of the nitrogen compound. Why? Two reactions. The first equivalent acted like what? A nucleophile. The second equivalent acted like a base. After it acted as a base, just a sec. After it acted as a base, what do we have?
Ammonia.
Ammonium. Can that act as a nucleophile anymore? Nope. So I kill half my equivalents by running the reaction with our nitrogens. Yes, Ree.
So before we were talking about how it would need a really strong base to deprotonate the amine. So itself is strong enough to deprotonate it then?
Is this an amine? Is our purple box an amine? No. What is it? It's not an amide. It's not an amide. Ammonium. Ammonium has a pKa of 9. Okay. Ammonium is relatively acidic. Okay. Or more acidic than our water molecules. Okay. This is one of the things that becomes tricky when you look up amines. If you look up the pKa for an amine, so we just say Google, find pKa amine. 9 times out of 10, the pKa you'll get will be 9. And you say, okay, well, that means the amines are acidic. That 9 is not applying to the amine. It's applying to the conjugate acid of the amine, ammonium. Why does then Google tell you it's 9? Because how do nitrogens act? As bases. So if you're looking at the pKa, they're giving you the conjugate acid for it because its standard chemistry is to act as a base, not as an acid. So it is very confusing with the nitrogens. Okay, so you have to be careful when you're looking up those pKa's. Did you get that when you Googled it? They tell you 9?
Yeah, the amine,
Yeah.
actually, the table I pulled up has the right one.
Oh, that's nice. Sometimes they give it, sometimes not. Okay, so you have to be careful with that. So that's what happens with your question. It's not an amine anymore, it's ammonium. That is actually acidic.
The protonated amine is 9 to 11.
So I got the 9 right.
The amine by itself is 35.
I got a 5 right. Okay. So, what's the issue between our starting amine and our ending amine? The starting amine has charge, so let's erase everything that's not those two. So there's our starting amine versus our ending amine.
Loses the hydrogen, brings the carbon.
Okay. What's different about its chemistry? What did we say was the chemistry of the amine? Nucleophilic and basic because of the lone pair. What's the difference between our starting amine and our final amine? Nothing, which means it's still reactive. That new product can react with another equivalent of the halide. What ends up happening? When we run this reaction, I don't get one product of the primary amine. I get the secondary amine, I get the tertiary amine, and I can get the quaternary amine. Is that a good reaction to run? No. That sucks. At best, we're getting a 60% yield. Okay, right out of the gates, we should be screaming that's a bad idea. So the nitrogen is not a particularly good nucleophile, okay, or ammonia is not a particularly good nucleophile because it will react multiple times with our electrophilic carbons. Okay? So when we're thinking substitutions, in general, bad idea. We don't typically want to do the substitutions with our amines. Okay. Could we somehow change the reaction so that I end up with just one product, though? How could I do that? Kind of. I just want one product. What could you do to get just one of those products?
Would you need something to neutralize the... so what happens is it's just, and then the amine deprotonates, and it keeps going.
So if we add an acid, that reacts with the base right away, and what happens to our nucleophilic character? Killed. That doesn't work. Okay. We could try and add a different base. Well, that still doesn't affect the nucleophilic character of the nitrogen. That just deprotonates that middle step faster. We might be able to kind of play with concentration things to favor one of those products over another, but there's another one. Could try and change the substitution pattern. I would say our first guess is, which of those products am I asking you to make? I didn't actually tell you. That was kind of mean. What's the issue with the primary? It still has that lone pair, and it is primary, which means there's very little steric hindrance. Regardless of the carbon structure I attach, the steric hindrance isn't going to be a feature, and it's likely to go on to the secondary. Okay? It's going to be less likely to go to the tertiary if I have a more sterically hindered carbon structure. So I could start to favor the secondary maybe a little bit, but I'm still going to bleed into the tertiary and quaternary.
Do you want to make it temperature affected? Do you lower the temperature?
Temperature could help, but I'm still going to get bleed over.
Couldn't you make it a worse nucleophile?
If it's a worse nucleophile, it doesn't react.
Changing the amount of it?
Which product do I want to make?
Why do you want to make it
Say that again, Corey.
That's where it stops.
I cannot do any more substitutions after I reach that quaternary state. So what I can do is alter the conditions so that I force the quaternary to occur. How do I force the quaternary to occur? Add more what?
Ammonia?
If I add more amine, that's the one doing the nucleophilic attack.
So you want to add more of the carbon?
I want to add more of the alkyl halide. If I add a ton of that in there, the primary may react, and I get the 57%. That's maybe my first round. But if I have a ton of it, I can run it a second round. What happens to the primary amines? They turn into the secondary. The secondaries turn into the tertiaries. The tertiaries turn into the quaternaries. The quaternaries can't do anything. Okay, that's my second round. If I have a ton of that in excess, I can move into a third round. Everything will shuttle till eventually it becomes the full quaternary amine. Okay? So when doing our ammonium substitutions, if we actually want to predict something, we will add a vast excess. Oh, shoot. Go away. Pause. Rewind. You didn't see that? There we go. We will add a vast excess of the alkyl halide, and what I end up with is the quaternary amine. What was special about our now quaternary amine? It is now a good leaving group. That structure could now potentially leave. Okay? It is so sterically hindered that it is probably going to make the backside of that carbon structure sterically blocked as well, which means if that is sterically hindered back here, what does that mean?
Can't do a substitution.
No substitution. Okay. So we could try and do something like an SN1. That's still not going to work well. Okay. The nitrogen's not good enough of a leaving group. Is there something else that competes with substitution? Elimination. How could we facilitate an elimination? Add base. Now we can go backwards again, or forwards again. If we add sodium hydroxide, that is a base. And heat, delta is heat. And we could now do the elimination. So let's go take a look at what we drew up. We had this guy, right, with CH3, all that fun stuff. Those are CH3s. Where would I expect the elimination to occur? What is that base going to react with?
React with hydrogen.
It needs to react with a hydrogen. Where are their hydrogens?
There's one on the carbon. Each carbon attached to the nitrogen.
So let's use different colors because you didn't suggest that carbon. If we remove hydrogen from the methyl groups that are attached, I know those look sloppy, but we'll come to an explanation here. Can we stabilize those electrons? No. So are those hydrogens acidic? No. So the blue hydrogens will ignore, those stay CH3s. What about the purple hydrogens? If I remove those, what can happen? It's not resonance.
It kicks it off.
Kicks it off, and I do my elimination reaction. So I could either reform what we'll call the purple product versus the black product. Does that color difference show up?
Yeah.
When we run those, what would we expect? Which product would we expect to be our final product? Why the black one? More stable, because it's more substituted. We'd say the black one is our product. That is exactly what Hofmann said too. And what happened? He was wrong. So he went back and proved why he got the purple product. We ended up with the least substituted double bond. He said, that's really weird. Okay, because it was so weird, what could he do? Poof, this is now the Hofmann product. Okay, he can attach his name to it because it's that bizarre. Okay, what you need to learn out of these nitrogens is really coming back to the Hofmann product. For lack of a better description, if you see nitrogen that's fully substituted, do the least substituted double bond. Just do that. Okay? Don't worry about understanding why, because the why, if you ask me, is very confusing to see. And it really comes down to, okay, yeah, we fixed all that. So we got our elimination. We end up with the anti-Zaitsev, which I hate as a word in general. I would just say Hofmann product. Okay? And the question becomes, why do we get that? Okay? That why explanation goes back to everybody's most favoritist thing from first semester, which was Newman projections. And we'd have to look at the Newman projections down the 1,2 bond or the 2,3 bond to see where that big old nasty leaving group is relative to the rest of the structure and the forming double bond. How many people actually want to draw that? Actually, I should put my hand down. I didn't think anybody really wanted to draw that. That's why I used the textbook slides. I stole the image from the textbook. Your textbook has a beautiful image of this showing that steric hindrance. If we look at the 2,3 bond, that would be forming the most substituted double bond. To get into the proper alignment for an E2 elimination, what has to happen? The leaving group and the hydrogen must be anti-periplanar. They're now aligned in that anti-alignment. What's the issue with this structure? We have steric strain. We have a gauche interaction there, which prevents the elimination. Okay? It never wants to make it into the anti-alignment. If it can't make it into the anti-alignment, I can't do the elimination. What happens down the carbon 1,2 bond? No more steric strain. We're in a staggered configuration. We can't really call it anti, just because of it's not anti. Okay? But we have a staggered configuration. That is lower in energy. That form can exist, which then means elimination occurs. I form the least substituted double bond. Okay? So the big lesson out of that, least substituted double bond when you're seeing these quaternary amines. Hofmann products. Okay, questions on that? What are the odds that I ask you to draw out the Newman projections on the exam? Okay. I'm not going to do that. I mean, I guess I could draw them, but I don't want to. Okay. Realize that if I make you do it, I'm doing it as well because I have to write the key. So if I don't want to do it, odds are I won't make you do it. Last part. Okay, of chapter 10, which kind of works out nicely for us. What is the reactivity of the CH group in this functional group? What is this functional group? Starts with A. It's an alkane. What do we know about the chemistry of our alkanes? Not really reactive. We have to do radical reactions. Okay? So what happens, though, if I bring it near, say, another functional group? Does that change the alkane's chemistry? Let's say if I made one of those H's, I don't know, a bromine. Does that change the chemistry? What does that change about the carbon-hydrogen chemistry? The hydrogen becomes more positive because there's this electron withdrawing effect. And what can now happen to the alkane portion of this? It can lose a hydrogen. We can take one of those electrons away. That would form a negative carbon, but negative carbons aren't good. So what happens? Fine. Electrons come down and we kick out the leaving group and we have, but I can't spell fast enough. I got to elimina before we got elimination. So we can get an elimination reaction. So we can alter the chemistry of that carbon-hydrogen bond by bringing it closer to other functional groups. Okay? What happens if we bring it near this functional group? What is this functional group? It's up two answers. We have a ketone, which is the primary whole structure, or carbonyl, which is just referencing the carbon-oxygen double bond. Okay, where is our alkane functional group? The ends. We have that hydrogen. If we compare that hydrogen to, say, the hydrogen up here, okay, both cases we're expecting the hydrogen to act as it is is a proton donor, which makes it an acid. Okay? We're expecting to remove those electrons and give them to our structure. And we would end up with a negative carbon. In the first case, with our halide, when we had the halide up there, we said that was really, really bad, couldn't do it on its own. It needed a leaving group to kick off. Okay? So we had to do a full-on elimination reaction. Okay? So we can't just do the acid base by itself. Can we do the acid base by itself now? What we end up with? Negative carbon. What did I have in the first case? Negative carbon. And when it was a negative carbon, what did I say? Not happening. So what do we think? Before we say it can't happen, we have to address what other things can be involved. And what are you suggesting we do, Jen? Okay. But then the carbon has too many electrons. Kicks them up to the oxygen. So I'm going to erase that arrow temporarily here. What is the relationship between those structures? Resonance. Can I just deprotonate? I'm forming a resonance stabilized structure. That resonance stabilization would suggest removing that hydrogen is possible on its own. The first case, I couldn't do it with the halide because there was nothing to stabilize the negative. I was looking at a negative carbon, and carbon can't hold a negative because not big enough and not electronegative enough. We drew this structure, we said, well, it's still carbon. Okay? But then Jen suggests we should look at resonance. And as soon as we look at resonance, we now have to pause and stop evaluating our negative carbon. We need to evaluate these two structures and say which one is the primary structure I should be looking at to think about stability. So which one? Why the second one? Oxygen can stabilize a negative charge better than carbon because more electronegative. Okay. Can I remove a hydrogen from an oxygen? Yeah. Okay. With sort of strong bases, but not stupidly strong bases. Okay. So yeah, that is a possibility. Okay. We have a neat little structure here. And Troy can help us out with this. That purple structure is the enolate ion. Okay? Because we have an ene and what could be an alcohol if we protonated it. When we now look at these two structures, which of those two is now going to be the reactive one? So that's a challenging question. Our reactive one is the first one, not the most stable one. Why? It's stable. It's not going to react. So when we're looking at our resonance structures, it's usually a good idea to look at, I never remember the correct phrasing, but I usually call it the first worst resonance structure. Because the first worst resonance structure sets you up with the reactive structure. The most stable one, or the best worst resonance structure. Because the stable one isn't going to react. We need to see those charges in there and know how they're going to predict and shift around. So we have our stable structure in the enolate in our purple. We have our reactive resonance structure in the red. What is special about the reactive red structure? Our carbon is negatively charged, which means I now have a carbon nucleophile. What can that carbon nucleophile do? Attach to, not necessarily other carbons, but if that carbon is a nucleophile, what should it be reacting with? Electrophiles. Do we have electrophiles already? Give me some lists. What electrophiles are we aware of? Yeah, it's a big one. As a hint, I already drew one up on the same slide. Alkyl halide. Good leaving group. I can do what type of a reaction? Substitution. Funny. What was the name of this chapter? Substitution. There it is. We now have a carbon nucleophile to do substitution reactions with our alkyl halides. What other common electrophile out there that everybody seems to be screwing up, particularly Tyler? Sorry to throw you under the bus. Earlier today.
And
Probably everybody screwed this up when they looked at the exam. What's our other common electrophile? Br2 is our common electrophile. Everybody looks at that and says, but isn't bromide a negative? Isn't that a nucleophile? Yeah, bromide is. Where's bromide? Not there. Bromide is made by reacting Br2 as an electrophile. This produces what as a product? Radical would be half arrows. Though it is an interesting parallel to the radicals, what did we do as a substitution? Shoot. Gave away one of the answers. What type of reaction is this? Substitution. What did we substitute? We did something for bromine. What was the something? Hydrogen. When do we substitute hydrogen for bromine? That's our radical reactions typically. We did not go through a radical reaction here. How do we know we didn't go through a radical reaction? Charge. The instant you see charge, you're not doing radicals. Okay? Those are the two primary reactions covered at the end of this chapter. So we see a big discussion on enolates, and then we react those enolates with alkyl halides. All we're doing is now adding a carbon as an extra piece. So if we drew that out, that would look just like this. Please check me on this, right? And then we just have those three carbons, 1, 2, 3, right? What was the? We missed one. One of the biggest mistakes that students make when we're looking at our enolates, you lose the carbon nucleophile. How can you ensure that you don't lose it? 1, 2, 3, 4, 5, 6 carbons need to show up in my product. 1, 2, 3, 4, 5, 6. Okay? So make sure you don't lose that enolate carbon. Questions on that? Okay. Yeah. Have we seen the enol and the enolate before? Yeah, we saw it with alkynes. Good guess. I mean, it is up there. In the presence of mercury. What did the mercury reagent do? Add, because it's an addition, OH and hydrogen to what? To nonpolar pi bonds. Is an alkyne a nonpolar pi bond? Yep. So what can it do? It adds H and OH to the nonpolar pi bond. And we end up with Troy? Because you're the one that pointed it out before. What do we have? In purple. Don't tell me a duck. All right, everybody see the duck? There's a little duck. No duck. What do we have? We have an enol. What can that do? Tautomerize to give us, and watch, I'm about to lose a carbon too. 4 carbons. And we end up with our ketone form. Okay? For those of you being like, oh God, I don't want to do this. Sorry. Start doing it, because it's going to happen again and again and again. Okay? So we have that tautomerization. This can happen under acidic or basic conditions. Should we walk through that mechanism? Is that a yes or a no? Yes. Okay. I'm actually going to say we already did the base one. Everybody confident with seeing the base one already? Yeah, we deprotonated the hydrogen first. Okay, then we made it to the enolate. How do we make it to the enol, though? Because we're saying base is needed to make it to the enolate. How can we possibly do it with the acid?
Add the hydrogen.
What's the most reactive thing? H plus. So what do we need to do? We need to react the H plus first. What's the H plus going to react with? Oxygen. We have the electrons on the oxygen to form. Does oxygen want to be positively charged? What does it do? It does what? Pulls the electrons. I'll accept that one. Donates was a bad word. Steals those electrons. We end up with positive charge on the carbon. What's the relationship between those two structures? Resonance. Does the carbon necessarily want to be positive?
No.
So what happens? Steals electrons from a nearby hydrogen. And we end up forming the enol. Notice H plus gets floating out there. And you might say, well, what picks up the H plus? What gave you the H plus to begin with? H3O plus, our solvent. When we removed that hydrogen from H3O plus, we made water. What could pick up that hydrogen? Water to reform H3O plus. Okay? Our acid is acting as a catalyst to facilitate and speed this reaction. What is the base acting as? A catalyst to speed and facilitate the reaction. Okay? So they can be either acid or base catalyzed. Typically, we see the enolate because our goal was to do what? Where? We wanted the carbon to become active as a nucleophile. Okay? To have a negatively charged carbon, should I be under acidic conditions or basic conditions? Basic tends to be easier to work with. Okay? Both work, but the acidic has limitations. The basic tends to run a lot faster. Okay? That's our tautomerization. So there's our obvious reaction. Okay? We're taking our keto form, and we can run under either acid or basic conditions. But again, the basic conditions make the most sense. We can do our substitution for that R group at the position next to our carbonyl, which is also known as the alpha position. Okay, so we're doing a substitution at the alpha position. Okay. Foreshadowing. We can do this with a really big fancy structure down at the bottom. Malonic ester. What is special about the enolate or enolatable hydrogen? Where is the enolatable hydrogen? I think I heard there's two of them. Right in the middle. What is special about those hydrogens in comparison to, say, the hydrogens off of our keto form? They're more acidic because resonance. We're getting sick of just saying resonance all the time. That means we can use a weaker base because they're more acidic, and we can do a substitution at that position for the R group.
Why does it say stronger, strong base then?
Stronger versus strong, which we will be addressing because that was addressed in the video.
So it still has to be a strong base.
It still has to be a relatively strong base. Yes.
It doesn't have to be a super strong.
It does not have to be a super strong base, or as I like to say, stupidly strong. Okay. What happens after that? All sorts of weird stuff that we'll learn about in Unit 3, so don't worry about it now. Okay? That's why the foreshadow. Okay? What happens if we go through and do it with our halogen? Okay, under acidic conditions, what happens? Okay, so we've got our answers up above, but I want to know the mechanism down below. How do you know it's acidic conditions? What's the most reactive thing present? What do you need to do? Protonate. What do we need to stabilize the H plus? Electrons. Where are their electrons? Oxygen. Draw the result. Ooh. Sorry, I just lost connection. But we're back. The oxygen want to be positive. No, so what happens? Steals the electrons from the pi bond, generating its, keep going, resonance structure. Thank you. Carbocation was valid. I just wanted to hear you say resonance again. I'm not hearing everybody say it. When everybody says it, maybe I'll stop asking. Okay. So we now have the carbocation. Is carbon 1b positive? What happens? We can remove the hydrogen, which is technically an elimination reaction, Jen. But referencing the bromine doesn't work out for us because the hydrogen is coming off as what charge? H plus. What is the charge of our bromine? What is the charge of our bromine? All except neutral. What's its partial charge? Positive. Can the bromine remove the hydrogen? No, because positive, positive.
And it's slightly positive because the electron density exists more in between the two bromines.
Yeah. And one is, as long as if we can bring the enolate or the enol structure closer to it. Okay, now what happened? Am I missing something?
Substitution.
Carbocation. Does the carbon want to be positive? What happens? Why resonance? Always resonance. That's why. Why the carbocation? The pi bond, those electrons were being shared between two carbons. We took those two electrons and we used them to make a bond between one carbon and the bromine.
Why wouldn't the
Which means
other-
what happened to the other carbon? Just a sec. It's missing electrons. That's why it's positive. Why did the bromine go to the the least substituted and not to the oxygen? The oxygen's already stabilizing the other one. Okay. We're trying to form the carbocation at the most substituted position. That oxygen is sharing electrons, stabilizing that carbocation formation there. So our bromine has to go to that position.
I was mainly referencing the other bromine that's non-negative charge. Why wouldn't-
So the other bromine coming in and reacting with that carbocation, we're going to run into some steric hindrance issues. And is it really all that positive?
Oh, because the resonance.
The resonance neutralizes that charge. So really that's not a good idea. Okay. Good looking out for it though. Does oxygen want to be positive? Nope. So what happens? Steals the electrons back from our hydrogen and we end up with so all of that and all we did was put a bromine on.
You would form another elimination reaction.
So now the question is, should we do it again? Okay. What initiated this whole cascade of reactions? Okay. The carbonyl compound had to act as what? As a base in that very first step. The H plus was the thing that initiated this. My carbonyl compound had to act as a base. Okay. What happens if I compare my starting material now to my product? Can I erase the mechanism? Okay. So what we said is we have a hydrogen here. Whoops, not even that. We can ignore that. We said that this oxygen was basic. Whoa, sorry, I didn't erase everything, so I'm going to have to kind of blindly erase. Oh, well, let me erase. Oh, maybe it will. Okay, sorry. That first species acted as a base, right? Everybody's okay with that? I am literally trying to erase blinded. Okay. So for this reaction to happen a second time, what has to happen? It still has to act as a base. Compare that structure's reactivity to our starting material. Is it more or less basic? Why is it less basic? We would hope resonance was the answer, but it's not this time.
Is it not more basic?
So we can start with charge. What's the atom that's acting as a base in both cases? The oxygen. Is it charged? Is the atom size different? Is the atom charge different? Is there resonance on that oxygen? No. Is there an inductive effect? Ooh. Our product has an inductive effect. What is that inductive effect doing?
It's pulling electrons into the
Pulling electrons into the structure. To act as a base, what does it have to do? Push the electrons out. As soon as we do the substitution, what happened to the reactivity? It becomes less basic, which means it's done. I do one substitution. Could we try and keep pushing it? Potentially. Or what we could do, this stupid erasing thing is really becoming irritating. Let's try this. Okay, now let's go back. What happens if it was basic? What's the first step?
It's going to pull off acidic hydrogen
Where's our acidic hydrogen?
attached to a carbon. So you get a elimination.
Careful, careful. You're going too fast for me. Form the negative charge. We've got our enolate, which is resonance stabilized in a pseudo-elimination. Can't really call it an elimination. I think when I called the last one an elimination, I was also wrong. Now what happens? What do we form? The exact same product. Which, is that a good thing? Shouldn't it be? The whole point of this was that we're looking at the enolate. How do we make the enolate? We can either go under acidic or basic conditions. So we should expect the same product, okay? At least once. There's the caveat. What did our starting material act as? It acted as an acid in this case. So if we now look at our product, we need to be looking at it acting as an acid. Which of those two structures is more acidic? Reactant or product? The product is more acidic. Why? The inductive effect. Okay. The hydrogen where the bromine is attached is more acidic now because that bromine is pulling electron density away because of its electronegativity, which makes that hydrogen more acidic, which means the instant I form my product, what happens? It reacts again. So when I run under basic conditions, I end up with two bromines.
Can you keep going though?
What do you mean?
There's two more carbons on the other side.
Two more whats?
I mean hydrogen.
Hydrogen's on the other side. Can it keep going? You are absolutely correct. Yes.
But it's
The
not-
final product we get, the fully substituted bromination product.
It's not going to do any of the hydrogen.
Why can it do the other ones?
They're not alpha carbon.
They're not alpha carbons. Why do we need the alpha?
Resonance.
Resonance stabilization through the enolate. Okay. So our base conditions react faster or quicker because we're initiating and making that nucleophile quicker. But the issue is that as soon as we put the halogen on, we just made it more reactive. It's going to continue to react until it's fully saturated. We've done the full substitutions all the way through. So when we're looking at those products and deciding what we're trying to do, if we take a look at my brief kind of spider diagram at the top, Br2 and acid, notice all I've done is put on a single bromine. The other one I also put on a single bromine, but I added no monosubs, meaning It keeps going. I can't add just one. Why did I not show them all? Because I'm lazy. Deal with it. Right? I don't know why I thought no mono-substitution was easier to write than just putting all the bromines on.
So in an
But I
acidic
did.
solution it does that, and then in the basic solution it fully.
Changes, yep. Okay. Where this is going to come into play is with this reaction, which is another kind of famous ACS question. They like asking this kind of question here. Okay. Methyl ketones can be converted into carboxylic acids if we use an excess of base and our elemental bromine or iodine. Okay. You don't know all of this reaction, but you know that first one. Actually, you know parts of the first one. What do we need to do with the base? Deprotonate. Where is there an acidic hydrogen? The alpha position. That can then substitute our OH4 bromine. Remember, the OH just pulls the hydrogen off, and we go through that whole cascade of brominations. But then, as Jen pointed out, this structure is now more acidic than our starting structure. So what happens? Pulls off another hydrogen, and that hydrogen then gets substituted with another bromine. And it does it again. Here's where we have an interesting issue, or an interesting thing appears. What can you tell me about bromine? It is a good leaving group. What else can you tell me about it? It's big. What does that mean? Or keep going. Steric hindrance, keep going. What's it connected to? Carbon. Carbon is relatively positive, okay? Particularly with all those bromines. Does carbon want to be positive? What does it start to do? Pull electrons. Can it pull electrons from bromine? No, so it's going to pull it from the only other atom it has access to, which is carbon. It's not connected to the oxygen. It can't take them from the oxygen. But then that carbon becomes positive. Do we have some negative floating around that could potentially help out that carbon? The rest of that mechanism, and officially even that part of the mechanism you're not responsible for, but what ends up happening is we end up taking off this last little piece as CHBr3, okay, or CHI3, or CHCl3. They're known as your chloroform, bromoform, or iodoform. As a class, they're known as haloforms. That is a haloform reagent that we've circled. Okay. What is special about that? It is exceptionally nonpolar. What can you tell me about our other product? The carboxylic acid, it's really polar. So they separate. When is this used? This is used to do a classification test for the presence of a methyl ketone. Do I have a ketone next to a methyl group? If it's present, I expect to see something come out of solution. If it's not present, then what does that mean? It's not a methyl ketone. It's a standard classification test the way it gets asked. Come on. Which compound will give the yellow solid HCI3 when mixed with iodine and sodium hydroxide? What is HCI3? It's the same thing as the CBr3 that we just looked at. What are they asking you to identify? Which of your possible answer choices is a methyl ketone? Okay. That's it. I didn't show any of the structures because, again, I got lazy. Okay. So, and we will come back to that one. So if we look at our enolate chemistry, in 2 minutes, because you guys have looked at the slides and you've reviewed this, you should be able to go through and draw out